Do I have to?
I got it.
You got it. Okay, announcements real quick, Potter internship, in case you didn't know, it is open until February 11th. So if you have a student interested in any kind of geoscience work, SciComm, any science communications, anything like that, we're focusing on the Red River Gorge area. And we're hiring 6 interns, so tell them to apply. Thank you. And Jason has a announcement.
Hi, I just got, huh? Oh,
Oh,
You
sorry.
have
Question.
a flyer or something that I can send out to?
We have a website, we have a graphic that Rebecca is not here. She can print it out.
Send those to.
You want the,
Yeah.
okay, cool. Yeah, I'll send an email. Thank you, Dina.
Yeah. Right.
okay, Mike told me I had to use this. So it's official. I just got done filling out doodle polls for the director search, and we have,
Thank you.
I think the announcement was just put out today or very, very recently for the job search. The week of February 26th, we're going to review applications. The week of March 4th, we're going to conduct Zoom interviews to narrow it down to a few candidates to bring here. And then somewhere between March 21st and 25th, we're going to have in-person interviews. And the hope is to have somebody in position by July 1st. Yes.
So the application window is only 4 weeks.
Blue. That's my answer is a color.
Is this a UK thing? Blue mean yes.
This is what I've just been told.
Okay.
That is my answer.
Okay.
I'm not commenting on the morality of such a thing. Any other questions? Yes.
Are the like section interviews part of those in-person interviews?
Unknown at this time, but I will definitely push for that again. What was the general feedback you guys had about that last time? Did you like having the chance as a section to talk to the candidates?
Oh, yeah.
I see yeses. Okay. So I will push for that again. If you have other opinions or questions, just email me or stop by my office. Don't drop it. No mic drops allowed.
Okay. No mic drops. All right, so hello, everybody. My name is Alex Washburn. And today I'm going to talk to you all about the utility of calcite veins, some sort of new methods that have been developed for calcite analysis, as well as their application to sedimentary basin analysis. But just kind of a plug, I'm going to talk about some research that I've done just as an example of how you can apply calcite veins to the real world. But calcite veins are ubiquitous. They're in like all kinds of geologic systems, from low temperature to high temperature. And so there's a ton more than we can do with them. And so in this presentation, I make a specific note to talk about methods of analysis that can be useful for lots of different stuff, not just for sedimentary basins. And then I give the research that I've done as sort of an example to work off of. And so since I'm fairly new here, I figured I'd do a little bit about me. So originally I'm from Farmington, New Mexico, Four Corners area. If any of y'all have ever been out there, pretty small town. And I went to Texas Tech University for my undergraduate degree in geology. I started when I was about 25, so I'm skipping a lot of history there. But after finishing my undergrad, I went to Brigham Young University in Utah for my master's degree, and then went back to Texas Tech for my PhD. And during my graduate studies, I did a bunch of internships. I did 4 internships with various oil and gas companies, and then I did 1 with the Department of Energy in Oregon. And then my wife and I both graduated with our PhDs. She does biomedical research, and then I did geology. As a family, we've got 1 daughter, and we like going to rock concerts. We explore national parks together. My wife and I ride motorcycles, and we ride for an organization called Bikers Against Child Abuse that we ride for abused children. And so that's just a little bit about me, just so you know. So I'm going to start off by introducing some questions that I'm going to try to answer in this presentation, and then introduce you all to the feature that I studied for my dissertation, which is called beef calcite, which is really interesting and fun stuff to talk about. And then I'm going to go over the methodology for my studies and introduce some of the new methods in geochronology and thermometry. And then I'll talk about beef calcites in the Heath Formation in Montana, beef calcites in the Wolf Camp in Texas, and then I'll go over a summary of everything. So there's any time that we're going to do any kind of research involving calcite veins, there's really two main questions to answer, and these are the two that I'm really focusing this presentation on. The first question is, what event does the vein represent? And really, this is a question you need to ask anytime you're going to do geochronology or thermometry, because this relates to what kind of question am I trying to answer about that geologic system, okay? And then the second is, are the methods reliable? Are they sufficient? Do I have enough context to be able to get a good interpretation? Because if I just try to interpret something based on one data set, almost always it's going to be wrong. Yeah, we'll go through all of this. So beef calcite veins. I'm guessing that most of y'all have never heard of beef calcites. Beef is the sort of colloquial term for these veins. The more technical name is bedding parallel fibrous calcite veins. Okay, that's kind of a mouthful, so I just call it beef because it's a lot easier to say in presentations and such. Plus, it's more memorable. But people would call it that because this stuff is fibrous and it kind of looks like cow meat, I guess. So these are just some examples of what that might look like. But the two important features are highlighted about beef calcite in that technical name. And the first is the fact that they're bedding parallel. Okay, so these veins always form along boundaries of mechanical weakness or bedding planes that were originally horizontal. And so then later they can be tilted or deformed. But they're always originally horizontal. And that's an important feature to consider simply because in order to get bedding parallel fractures, you have to be able to overcome overburden or like lithostatic stress, all the rock that's laying on top of you. You have to be able to lift all of that up in order to get a horizontal fracture, okay, in order for the vein to form inside of it. And so originally, people would think that these veins only formed in a shallow subsurface, like less than 500 meters of burial depth, to overcome just a little bit of overburden. We found out later that these veins can form at great depths, greater than 4 kilometers of burial depth. So overpressure is important. And in case you don't know what overpressure is, so this chart on the right here displays this blue line represents hydrostatic stress, which is like the normal pore pressure of water in the subsurface. And then this black line would represent lithostatic stress, and that can move depending on the density of the rock that you have over your head. And then overpressure is defined as anything in excess of hydrostatic pressure, okay? And so that's the most important thing that contributes to the formation of beef calcite. Another thing that can contribute to the opening of horizontal fractures is called seepage forces, okay? Seepage forces form whenever there's a large pressure gradient. So if there's a high pressure zone in the subsurface overlaying by a low pressure zone, the fluid is naturally going to want to migrate upward into that low pressure zone. So the actual migration of those fluids upward has an upward force. It's exerting an upward force on the rock that can make the formation of or opening of fractures, horizontal fractures in the subsurface possible. Okay. This also works with like buoyant migration of hydrocarbons in the subsurface. If they're moving up, that also does some seepage force. So the greater the overpressure, the greater this pressure gradient can be. So then the greater the seepage forces can form. So overpressure, still the most important. Tectonics is also a big contributor. It doesn't always have to be there though. What tectonics can do is if you have shortening, horizontal shortening in the subsurface, then it reorients the stress fields in the subsurface so that, you know, you're taking it from say an isostatic stress field to one in which the least principal stress direction is in the vertical. Okay, so the least amount of stress is coming in this direction. So if the least amount of stress is in the vertical, then you can open up horizontal fractures easier. If it's shifted the other way, if the tectonics are more extensional, then it's more favorable for vertical fractures to form. Okay. So one other note is that when you have horizontal shortening tectonics going on, the amount of overpressure you can build up is actually increased as well. So again, overpressure is still a big deal. Okay. So this is what beef calcite fibers look like. They precipitate in this fibrous texture in two primary morphologies, the sort of parallel fiber habit, and then what they call cone and cone. But the important thing to note about both of these textures is that they're thought to be primary growth textures. So if you recognize beef calcite that's fibrous, that is a primary texture, then the event that you're relating it to is the original event that caused that beef calcite to precipitate. It's not a replacement texture or something else. So that was important for the question to answer for our number one question. What do you think? So now I'm going to talk a little bit about methodology of how to analyze these beef calcites in particular, but also really any calcite that you're going to do work on. And I wanted to go over this mainly because I think just my general feeling is that a lot of people avoid doing research on calcites, at least geochemical research, just because the calcite can be such a messy system to work in, because it's unfavorable for geochronology, or because it's so susceptible to alteration or deformation. It's a really soft mineral. And so things can get really complex with diagenesis and all this other kind of stuff. So I'm hoping that as I go over these things, y'all will feel more comfortable with the idea of doing research on this stuff so that we can collaborate in the future, right? So first of all, whenever you're going to study any kind of calcite feature, you want to make some large scale observations, whether you're looking at it in core or whether you're looking at it in an outcrop. You can get an idea of maybe the orientation, the veins themselves, if there's any deformation features. You can get an idea of relative timing in comparison with other veins that you might see in an outcrop, stuff like that. So as much contextual information as you can get out of it. Then you want to put it in thin section, and you want to look for things like microstructures. People will publish whole papers just analyzing microstructures in order to reconstruct, you know, past stress fields and tectonic deformation in the subsurface. But for geochronology, one thing that I would be particularly concerned about would be multiple generations of vein growth. So in this example, this vein has two generations, an inner generation here shaded in gray and then an outer generation shaded in white. And so I'd want to know this before I do geochronology on it, because one generation may be significantly younger or older than the other generation. So I'm going to want to make sure to account for that. So again, contextual information is very important. And then there's a whole suite of elemental or chemical characterization that can be done on these veins, including cathodoluminescence, which is really cheap and easy and fast. And this is a beef calcite vein from the Heath Formation, where you know, I was able to really easily identify this sort of symmetrical compositional zoning here based on the CL imaging. So I labeled them, you know, this orange zone, this brown zone, yellow zone, bright yellow zone. It sort of suggests that there might be symmetrical growth in these veins, starting this maybe across this median suture. Stable isotopes are always good to use anytime you're going to be studying calcite. But again, the interpretation of stable isotopes really needs a lot of context. So you make sure that you're interpreting it in the right frame. In this sense, I was able to use them to support the idea of symmetrical growth, because when I did stable isotopes across the vein and along the vein, I found that it was still symmetrical across the median suture for the most part. And then if you really want to get into the weeds, you can do things like electron probe, microanalysis, in order to get more detail about the chemical composition of the calcite, to make sure if it's actually not really a calcite or it's a high mag calcite or something else. In this example, I was able to note this sharp compositional boundary between the bright yellow zone and the yellow zone. That turned out to be important for the interpretation of some of my geochem data. I'm not going to really go into the details in this presentation just because I don't have enough time, but just as an example. And then scanning electron microscopy. This was really important for me because I was going to do geochronology, because I was worried about inside these beef calcite veins, there's like a ton of inclusions. Okay, this is calcite, most of this material is calcite, but all this darker stuff would be like included clays, organic matter, quartz, sometimes dolomite. That's all stuff that I needed to worry about when I was doing laser ablation of my calcite geochronology, because it was a potential contaminant, right? I didn't know how it was going to influence my geochemical results. So I needed to account for that. Okay, so geochronology. And if any of y'all are familiar or heard anything about trying to use uranium-lead geochronology in calcites, if you ask somebody who's tried this, they'll probably tell you like a typical failure rate, somewhere between 70 to 90% failure. That's a really difficult system to try to do geochronology in, and for many different reasons. The sort of accepted way, or the easiest way to do it nowadays, is using laser ablation, inductively coupled plasma, mass spectrometry, using something really accurate like a single collector mass spectrometer, not like a quadrupole or something like that, just because there's such low abundances of uranium. But if any of y'all are familiar with or fans of the 90s X-Men cartoons, you know that Wolverine can actually smell lasers, which William Frederick Herschel, I think his name was, he says, no, you can't do that. That's too far beyond reality. Whenever we use lasers on to do geochronology, like if you were to do it on a zircon, which zircon is like the greatest mineral ever, right, to do geochronology on, you can do a really small spot size, maybe like 7 microns across, to get a really good signal. But in calcite, because the uranium is so low, you have to use ginormous spot sizes. So like 60 to 150 micrometer diameter spot sizes is typical. I've seen them as big as 180 microns. And just in the laser ablation world, that's like ginormous, okay? But this is, you know, what a laser spot might look like. You can use them in a stationary spot. Whenever I did it, I used them in line scans, just because it's better for a lot of different reasons. But whenever you get your signal coming out of this, this is what a typical signal might look like from a calcite. And this is an actual signal that I took from the Heath formation, where we have uranium in blue, lead is in red, and then it's counts in the y-axis, and then versus time. So you get sort of this time resolved analysis, right? But then if I was doing geochronology on a zircon, I would just basically, in my data reduction, I would just average out the lead and uranium isotope ratios across this entire signal. But we're not working in zircon. This is not as favorable of a system. So what we do is we select these really discrete intervals, like for example, this peak here, and that uranium lead versus lead ratio is what we plot on our isochrons. Okay, just these little discrete sort of time or signals. And but there's some potential problems with that, because if I'm only selecting discrete little peaks, what if I get a signal like this that looks really convoluted, and it's really like there's a ton of different peaks, these signals are all mixed up here. So do I select all of these peaks together? Do I select, you know, this one's got better uranium versus lead, so do I just select a portion of this that's more favorable? Do I select these multiple peaks? So you can move this stuff around a whole lot, okay? And so whenever I was doing this work, I found that it can almost be extremely subjective. And so just as a thought experiment, I took one of my veins from the Green River Formation and I thought, I just wonder how many different ages I can get out of the same vein that are not like completely ridiculous. And so I'm gonna show you 4 different ages I got from one vein. And this one was, the top of the screen is cutting it off, but it was like 1.6 million years. Yeah, I got another at 8 million years, plus or minus 3. I got another that was 32.5, plus or minus 2, and then a fourth at 49, plus or minus about 4 million years. So really what I learned when I did this thought experiment is that reality can be whatever I want. Which of course, it doesn't take it to your chronologist to say, no, that's not how reality works, right? So I realized that I needed to develop some kind of a philosophy by which to consistently analyze these veins so that I can get consistent results and so that it's not quite so subjective. And so I thought, I took my signal here and I separated it out into 3 distinct domains that I could use in my data reduction, okay? So 3 types of signal selections. The first would be if I saw there was a peak in uranium, but there was no correlated peak in lead, okay? The second was if I saw a peak of lead, but then there was no corresponding increase in uranium. And then the last was both uranium and lead. There were peaks for both of them that sort of correspond, okay? And so whenever I did this, I assumed that the problem with my samples was that I was hitting inclusions. Because as I'm doing laser ablation, the laser is drilling down and I'm moving the laser. And so who knows how many inclusions I'm hitting because I can't see everything in the subsurface of the sample. And so I thought this would be a good method to account for that. Well, what I found was that whenever I plotted all 3 of these types of signals onto an isochron, that they're all the same age, they're isochronous. And whenever I included all 3 types of signals, it gave me much smaller errors. So I would get the same median age on any one of these 3, but it would just reduce the error because it would improve the spread in the isochron, okay? And so where I really get problems, I found, is whenever I try to incorporate something like this, where there's like misaligned peaks, or maybe this one over here with the lead doesn't quite line up with the uranium. If I try to incorporate that whole thing, it'll give me an anomalously old or an anomalously young data point, okay? So it's kind of mixing up signals. And I've got a few theories that I want to test about that, but developing this philosophy, I feel like this is a better way to do it. And okay, so the next thing I want to talk about is doing thermometry on these veins. So there's 2 primary methods that I know about that you can do thermometry on. And the first is fluid inclusions. I'm hoping that y'all are more familiar with fluid inclusions since we have an expert here in KGS who does fluid inclusion analysis. And it's been around for a long time, a lot longer than the other method I'm going to talk about. So maybe it's more familiar, so more people feel comfortable with it. You can potentially get more data out of fluid inclusions, like what the fluid is actually, what the composition of the fluid was, like what its salinity or isotope composition was. But sometimes in carbonate veins, there might not be any fluid inclusions, or they might be inappropriate fluid inclusions, like single phase hydrocarbon inclusions. You can't get a temperature from that. So one other method to be able to use is called clumped isotope thermometry, which is a relatively new method. Maybe in the past 20 years it's been developed, and there's been a lot of development on it. Andrea, if you watched her presentation, talked a little bit about clumped isotopes. I think she used this exact same figure actually. But the theory behind it is that the bonding of the heavier carbon isotope to the heavier oxygen isotope in carbonate is a thermodynamically driven process, where the colder the temperature, the more of this clumping you're going to get. So we can take that carbonate dissolve it in acid, get CO2 out of it, that preserves that clumping, and then analyze it to get a temperature. And you always have carbonate material if you're studying a carbonate vein, so it's always possible. So it applies to any calcite, really. But one of the downsides of it is that it takes a pretty large sample. So like in conventional isotope analysis, these little tiny drill holes is what I did for my conventional isotopes, and that requires like maybe 0.1 milligrams. If I were to do clumped isotopes, that requires maybe 50 to 100 milligrams of sample. So it's quite a lot. So you can't do this method on like really small discrete features, okay? Like tiny little fuselinids or something like that. It's only for big stuff. So veins, it works pretty well on. There's also some concern about erroneous temperatures from clumped isotopes from things like solid state reordering. Basically, the system is susceptible to being reset if the vein is exposed to like a much higher temperature for a long period of time. We're still developing ways to test for that. But the way that I would suggest test for that, plus the validity of my uranium lead geochronology, is to just use multiple methods that validate each other, okay? So whenever I analyze my beef calcites, I suggested that we do uranium lead geochronology to get the age, and pair that with clumped isotope thermometry to get the temperature. And I also did conventional isotope analysis of oxygen and carbon isotopes. So then I can interpret in a good context the age, the temperature, and the fluid source. And so all three of these methods really should support each other. And they would verify, you know, whether I was getting some weird result from one of those methods, right? So now I'm going to talk about some of those studies that I've done. And I think I'm doing pretty good on time, but I'm going to start off with the Heath Formation in Montana. In Montana, the Heath Formation comes out of what's called the Central Montana Trough, which is sort of a structural feature. It was a failed alocogen that's like a Precambrian age that was then reactivated during the antler orogeny in the Devonian. The Heath Formation itself was deposited in the Mississippian, and it's a really organic rich mudstone. So it's like the main petroleum source rock for this area, and they do produce oil out of it. The structure of that is really defined by continued subsidence since its deposition, and then basically a structural inversion during the laramide orogeny. So I took all the beef calcite from that, from the Heath, out of the upper Heath Formation, from this well, the Flat Willow well, and I took like, I can't remember if it was 6 or 8 veins out of like a 10-foot interval. There was no other beef calcite in all the rest of that core, which I found interesting. In order to interpret the time, temperature, and source of the veins, I decided to first be able to put it into context on a burial history diagram. So I made this burial history diagram using Platte River Associates Basin Mod software. And I used primarily well logs, like mud logs and wireline logs, to get the current, like the present day stratigraphy. And then I looked at preserved strata and nearby uplifts. A lot of tectonic uplifts in the area preserve all this Cretaceous strata, while it was all completely absent in my well, a huge unconformity in there because of the inversion during the laramide. And then I had organic maturity data that gave me a good idea of how deep the rock had been buried. So how high the temperature had got, which indicated that max burial was at about 2.2 kilometers. This is the Upper Heath Formation right here. So at about 2.2 kilometers. I can't draw a straight line in this. But one thing that I did that was sort of new for the Heath Formation when I made this was I attributed this intense burial event here to the severe orogeny, because the severe orogeny front is just to the west of the Central Montana Trough. And so I classified the trough as a foreland sedimentary basin. So I did uranium lead geochronology on it using my devised philosophy of data reduction. And I got 3 successful ages, ranging from, this one's 121 million years, 96 million years, and 101 million years, and plus or minus about 20 to 25 million years, which that might seem like a pretty big plus or minus. These errors, which are plotted on this diagram here to show the variance of time possibly. But this is actually a really good error for uranium lead geochronology for calcite, okay? I've seen published errors that are like 80%, 90% error, which is really huge. It makes the date pretty much unusable. In this sense, it's very usable because it places all 3 of these beef calcites within this rapid burial event during the severe orogeny. So let's check it to see how accurate that is. I also got my clumped isotope temperatures, and those temperatures range from 43 degrees Celsius to about 52 degrees Celsius, plus or minus 2 to 4 degrees. And so what's important about this is that they match the burial temperature, what I would expect the temperature of that rock to be at this time. Okay, so comparing it to my burial history diagram, if this is, you know, at about 1.8 kilometers, let's say, during this time, then I would expect to see a temperature of about 50 degrees Celsius at the geothermal gradient of 25 degrees Celsius per kilometer. So the other thing that was of note was that the age correlated with the temperature. So the oldest age gave me the lowest temperature, while the youngest age gave me the highest temperature. So that supports the idea that these veins were forming as the formation was being buried. So all these methods are kind of validating each other, right? It works. So maybe my age is real, maybe the temperatures are real. And then to take it a step further, I did stable isotope analysis where I noted these 2 populations of isotope within the calcite veins. And at first, the bulk of the population I interpreted to come from bacterial consumption of organic matter that fractionates carbon mainly and oxygen isotopes in a certain way, that these are the values that I would expect to get out of it. I would go into more detail, but I really don't have enough time. So really what this did is validate again, another point of validation that this data is real. So in summary, for the heat formation, I concluded that the severe orogeny tectonics were actually important because they provided favorable conditions for the opening of those horizontal fractures. Then I said the overpressure probably came from disequilibrium compaction. Whenever you have really rapid burial, the rock doesn't have enough time to equilibrate its pressure. And so that's what can lead to really significant overpressure. And then so the age, the temperature, and the carbonate source all agreed with a burial depth from about 0.8 to 2 kilometers. So they all ratified each other. And then to take it a step further, this particular well was a dry well. It was a wildcat well drilled back in the 80s, I think. And it came up dry. And while other wells in the area do produce a lot of oil, in this sense, I suggested that because the overpressure developed earlier and there was a really short residence time at the maximum burial depth, the overpressure actually suppressed the generation of hydrocarbons, so it didn't make any oil. Okay, so then we'll talk about the Wolfcamp. This one is my favorite one, and there's way too much data on the Wolfcamp for me to talk about all of it, but I'm just going to try to hit the highlights. But if y'all have questions about it, I would love to answer all of them. So if you're not familiar with the Permian Basin is in Texas and New Mexico. This is the border of New Mexico right here. And it's a very well-studied basin because it's such a huge producer of oil. I think that it surpassed the Ghawar oil field in Saudi Arabia a couple of years ago in its oil production. And so it's like, if it's not the biggest oil field in the world, it's up there. And really, the Permian Basin is subdivided into several sub-basins, including the Delaware, and the Midland basins. Well, the beef calcite that I studied, I took out of a ConocoPhillips well in the Delaware Basin. And in the Delaware Basin in particular, there's two areas of ongoing debate. Okay, the first is about overpressure. All of these units, I don't know if y'all can see this because it's kind of small, but this is the Wolfcamp right here, and then all the way down to the Mississippian limestone, or sorry, actually the Woodford and the Devonian. All these red stars represent units that are overpressured today. So really high formation pressures in the subsurface. And so a lot of scientists actually believe that that overpressure developed back when this basin was first being buried, which was like 300 million years ago. And so there's a lot of other researchers that say there's no way that overpressure could persist for like 300 million years. That pressure would slowly bleed off over time. And so long-lived overpressure, they say, is a myth. The other area of debate is people have done a lot of organic maturity studies in the Delaware Basin and found that the organic matter is really hot. It's really mature. It's more mature than the current burial would account for. So they say it was either the basin was hotter in the past or it was significantly deeper in the past, right? So, and they're not quite sure which is which. There's some debate on that. So I used my beef calcites to improve the burial history of the Wolfcamp. And so I'll show the burial history last instead of on the heath. I showed the burial history earlier. But the first sample, the first vein that I tried to do calcite geochronology on from the Wolfcamp gave me an age of 373 plus or minus 243 million years. So it's got to be apparently older than the Wolfcamp itself. And obviously with an error that large, this date is completely unusable. Okay, so that I would count that as a failure. The second vein that I dated gave me an age of 185 million years plus or minus 120. That's not the worst error that I've ever seen, but it's still pretty big. But that error is just because these samples in particular were very, very low in uranium. Yeah, I'm talking like 0.03 parts per million, something like that. But I mean, the median age, 185 million years, at least that's actually possible. So I felt kind of like, it's not great, but it's not horrible. So yeah, high common lead and low uranium. So I just got on this isochron here, it's just a really bad spread. Look at these, the size of these ellipses is dictated by the error in the isotope measurements. And these are just ginormous. That's why the error was so big. So an insufficient spread for an accurate age. So then the third vein that I dated, I got 153 plus or minus 53 million years, which it's a reasonable error for the age. Okay, it's like a 30% error, which again, that's actually pretty good and a reasonable median age. So we got one. So only two of them failed and one of them worked. But at 150 plus or minus 50 million years, because we've already established that we have to have overpressure in order for these veins to form, that means that long-lived overpressure is very likely. That means it persisted for at least 100 million years, maybe 200 million years. And honestly, the overpressure probably developed long before this vein formed. So, boom, roasted. For all those people who doubt long-lived overpressure. Okay, so then I did my clumped isotope thermometry, and the temperatures I got ranged from 142 to 161 degrees Celsius, plus or minus like 13 to 15 degrees, pretty reasonable. So they were all successful. And I compared those to, we did some fluid inclusion analysis just to see if we could get another temperature out of these veins. And actually, we did the fluid inclusion work long before we did the clumped isotope work. But we didn't find any appropriate fluid inclusions that we could get temperatures from. Instead, we just found these single phase hydrocarbon inclusions, but some of them fluoresced, which means we could do Raman spectroscopy on them, and we could try to get an idea of what was actually in those inclusions. And they were mature gas or sorry, early condensate gas inclusions. So they were methane that had a little bit of like N-alkanes and other longer chain hydrocarbons in there that would have originated in the early condensate window. So at about 150 degrees Celsius. So those types of fluid inclusions would come from exactly those temperatures that I got from my clumped isotopes. So we have some validation that the data that I'm getting is real, okay? And then as a third point, for the stable isotope work, I did some on my own veins, but sorry, this guy, Dauber and Goldstein from Kansas in 2020, they studied a whole bunch of wells in this area here for the wolf camp, and they put together a whole sequence of diagenetic events that included beef calcites. When I compared my data to what he had done, what I found was that all my data aligned with where he placed his beef calcites that he analyzed. He didn't get temperatures from them, but I did. And using his data and mine, I was able to determine that the beef calcite represented the thermal maximum of the basin. That's as hot as it got before it started cooling down after he got these other temperatures from fluid inclusions from other calcite features. So using all of this data, I was able to improve on the burial history of the Delaware Basin. So these are what the burial histories look like, the published ones, before I did mine. And the only thing really to note is that in both of these, the maximum burial was during the Cenozoic, so much more recent maximum burial. Whenever I adjusted mine, I used my beef calcite that represented the thermal maximum, which again, even though these are big errors, it still places it well within the Mesozoic, okay? And so I placed my maximum burial in the Mesozoic, and then I also had some appetite fission tract analysis data that I included in here that suggested an uplift in the Cenozoic. It also suggested a normal geothermal gradient in the Cenozoic. But some other people had done research previously. They were able to constrain that sometime in the geologic past, the paleo geothermal gradient in the basin had been way hotter, like between 30 to 54 degrees Celsius per kilometer, which is really hot, okay? But they didn't have any kind of time constraint on that. So based on the data that I had, I said, well, it's probably originated during the tectonics of the Marathon Ouachita orogeny when this basin was really forming. And then through time, it cooled until the formation of the beef calcite at a geotherm of 30 degrees Celsius per kilometer, and then continued to cool until our present day, or close to present day values of 21.8 degrees Celsius per kilometer. So really, even if you didn't follow all the details of this, I'm just demonstrating that there's really strong utility for these veins, or for really calcite veins in a multitude of systems. So it supported long-lasting overpressure. It placed the basin thermal maximum in the Mesozoic, and gave me a much higher resolution basin history, including my my AFTA data. And then so now I'm just going to summarize all the things that we've learned about calcite, and hopefully answer the two questions we started off with. What event does the calcite vein represent? In the peat formation, it was a certain burial depth, 0.8 to 2 kilometers during overpressure and the foreland tectonics of the severe orogeny in that basin, which I then used to improve our tectonic and our hydrocarbon maturation histories of the basin. And then the Wolfcamp formation, that formed during the early gas condensate window from a combination of diagenetic and disequilibrium compaction overpressure. And then I used that to resolve the burial history diagrams for the Delaware Basin, which impacts you know, our understanding of the petroleum systems there. So also did we sort of resolve some fears about the methods that we can use to study these veins, hopefully I was able to propose a new method for data reduction of geochronology that made us all feel better, less subjective. And establish that the more context that we get on these veins, the better the interpretation is going to be, the better we're going to feel about it, and the more utility we're going to get out of them. So I suggest using at least time, temperature, and source analysis for any vein that we're going to examine in the future. And so I'm currently working on 3 additional veins from 3 more sedimentary basins in the US. I proposed a study to the NSF for a more systematic analysis of the uranium lead system in calcite veins. And then I've also found a whole bunch of beef calcites in the Ohio shale. Thanks to Brian, he helped me find all of these. So there's potential to be doing this kind of work here. And then hopefully at some point I'll be able to expand my expertise beyond just these types of veins into lots of different kinds of veins. So thank you very much. Questions? Perfect, right on time. Zach?
How big a spot size did you use for that wolf camp?
The wolf cam is a bigger, I used like 150 micron. I tried to get away with 120 and even that wasn't big enough, so I had to step it up to 150. So yeah, it was pretty big. Yes.
What interval and what is it in, or are they all out?
What interval of the wolf cam? I didn't really want to say what interval they were in because it's almost really subjective depending on which oil company or which geologist even is doing this photography on the Wolfcamp. There's Wolfcamp A, the Wolfcamp B, the Wolfcamp C, the Wolfcamp D, and really from one company to another, it's really inconsistent. So I didn't bother. I just said I took them from this depth, from this well, so they can figure it out themselves. But so I'm not really sure which interval it would actually be from. Anybody else? Yeah, go ahead, Steve.
So I'm interested in your horizontal fractures. Are these along bedding planes, I assume?
Yeah, always along the bedding planes.
And just that overpressure causes those horizontal fractures.
Yeah, I mean, you have to have the overpressure, because even if the fracture were to open, you didn't have enough pressure, the fracture would just heal up, it would close back up. And so, yeah, and overpressure we think is enough by itself to cause the fracturing. The tectonics helps, and the seepage forces, I mean, it's kind of hand wavy, but maybe they're there, maybe they help. So, but really, yeah, overpressure is a big thing.
So I have a master's degree, and I'm kind of learning about joints, okay? And so just from what I learned in school and my reading, I'm like, okay, we've got hydraulic stresses, we've got tectonic stresses, different form joints. We can get joints from unloading and release. And this is the first time I've realized that you can get it from compression as well.
Yeah, and it's not the overburden itself that's allowing these fractures to be created, because anywhere in the subsurface, we're gonna have some amount of overburden.
Right.
But, it's that overburden that we have to overcome by the overpressure that allows the veins to be formed.
Right.
So, yeah, it's, and there's a lot of,
Plus all the joints I look at are almost vertical, you know,
Yeah.
if they're inclined, you know, in my mind, I'm not necessarily looking for horizontal joint.
yeah,
Sorry.
I have a lot of climate experience too, so we're the same on. Yeah, go ahead, Marty.
So, one thing I would do, especially since a lot of these pieces are more cancer system, or is that you might want to lower get simple phase the gas are. So someone knows what to do with them, actually material like gas. I would talk to you more about that. But the one thing I would say is that, when I looked at the rain lead data, seems to me like we got a decade of a big issue here. That issue is how do you actually account for analytical error instrument versus the actual error you get in the sample. But what I was seeing is, basically a lot of worries. And not only that, when you're doing the sample,
Yeah,
I don't know if these things exist in that community, but some samples are out there that have built that ratio. Actually, I
yeah, absolutely. So your question is about, how do we deal with the analytical errors within laser ablation, uranium lead geochronology, and, particularly with calcite. The way that we deal with the analytical error is that we have one standard that works really well, and it's from the Guadalupe Mountains in West Texas. That's our analytical standard that we correct all of our uranium isotope ratios to, and it works really well. We also have a bunch of secondary standards that we run alongside our primary standard. We don't use them for corrections, but we use them just to make sure that it is giving us the isotopes that should be there. So they're just validations. And then for the lead isotopes, we use a glass standard. It's one of the NIST like 614. So that's how we deal with our internal analytical errors. And then as far as using a static spot versus a line, the problem with using a static spot is that you're still drilling down through material, just like you would be moving the spot. You're still getting a variety of material, but whenever you drill straight down, you can get downhole fractionation effects where the laser coupling with the sample can actually begin to melt the sample, and that will fractionate the isotope signals that you're going to get out of it. You have to correct for that, which again is what we use the standards for. But if you do it in a line scan, you don't have to worry as much about the downhole fractionation effect. It almost completely gets rid of that. And that's why I say there's a lot of people who prefer using the static spots. But analytically, it's so much better if you move the spot so that you don't get that downhole fractionation. So hopefully that answered your question. But, go ahead, Mike.
So my question is like, how, when you initially start your analysis of the calcite, how can you test whether or not it's behaved as a closed system or an open system? Because ultimately you're making the assumption that what you want to know is, the timeline of formation, but that presupposes that in fact that's closed system is sensitive. How can you test for whether or not it's transition between closed and calcite?
Yeah, that's a difficult question to answer, right? Whether or not the calcite behaves as an open or a closed system since it's been precipitated. And I think we just try to do all of the due diligence that we can, like with the textural observations to see if there's any kind of replacement textures or dissolution, reprecipitation, try to rule out things like that. And then if the system has actually been altered, like in a solid state, which apparently can be a problem, especially with the clumped isotopes. And so maybe it also has a problem with uranium lead. We don't know. I don't think so. But really, we count for that by if the isochron fails, basically, then it could have been because of some disturbance of the system. But I don't think that our analysis has really been precise enough to be able to say that that's true or not. Because first of all, our errors are so large that even if there was a little bit of lead loss or something like that, we might not even be able to tell, because we get such big errors anyway because of how little uranium is already in that system. But based on work that's been done on the really high precision isotope dilution stuff, we have some basic understanding that whenever we are able to at least identify that there's no replacement or deformation or stuff like that, or dissolution, I mean, that the system should still be intact and give us really good isochrons. So that's the best due diligence I think we can do at this point. Yeah, thanks. Tony. Go ahead, Vincent.
I want to ask about that in my question as well. At that size, and like you looked at 8.6 at one point, used for age sampling, I think it's all in the information. The fact that you're doing all of them, I'm assuming in line, is it difficult to try to find spots to know whether sort of purity in the calcite? How'd that process go?
Yeah, so finding like where I'm gonna plot the spots.
Yes, and across the whole line, yeah.
Yeah, so, an interesting question, because whenever we do laser ablation on the thin sections, what general research has found is that there's not really a good way to be able to tell where to put those spots where you're gonna get favorable uranium amounts.
Sure.
Versus like super low, and so I definitely found that to be true. I would just put plots all over the place. I would stick the lines from the very edge of the vein towards the middle and all the way back over to the other edge. And just try to spread them out, and I would do a lot of them, like 30, in order to try to get enough data so that I could get a nice isochrone out of it. Because like you saw from that signal, most of it is like basically nothing in there, no uranium, no lead, until these little peaks. People have found that that's what's to be expected, is that it's almost like the uranium and lead are in these discrete little bundles, just like somewhere in that calcite. And so you just put enough plots on there and hope that you hit them, and they are able to get enough data to be able to make a nice isochrone out of it.
And I never really heard of that moving line sort of thing. Is that because of the calcite system specifically, or has it been used in other?
Oh, no, they use it in a lot of different stuff. In fact, they've recently, within the past maybe 5 years, they've developed these rapid washout stages so that you can shoot a laser at a system and move it really rapidly, and then basically build a map, like an isotope map from your sample. And so some people use that in calcite geochronology because there might be distinct time domains really close together. So they'll just map them all out, which is cool. I can do that. Yeah, no problem. Jason.
Just all my questions, I don't have you, or has anybody kind of, took the laser to some of the inclusions specifically to see what signal you get? Because if you're measuring like, 30, 40 spots on a slide, right, from end to end, if you know what your inclusions are giving you might still get like little mini bits conclusion or something definite at the surface, right? You might be able to take like some sort of quantile approach, like the higher or low quantile of your group of 30, maybe more accurately isolate just the calcites.
Yeah, and I'm sorry, the question that you asked for those that are online was about if anybody's really studied the inclusions by targeting them specifically in the laser. And what I can tell you is that there are researchers who have specifically targeted like fluid inclusions with the laser, or they've done things on similar minerals like clays or quartz or whatever. But they've never really done that research in connection with geochronology. And that's actually what the proposal that I wrote to the NSF was, so that I could do a more in-depth study of exactly what those inclusions are doing to our signal. So yeah, you stole my brainwaves. Yeah, and I'm really hoping that I get that funding, because like it'd be a really awesome study to do. But we'll see. Yeah, go ahead, Mina.
Two questions. One is super easy, which is just your data reduction methodologies are published already.
Yes, my data reduction method is published. It's in that paper that I just barely published online.
For that proposal.
Yeah.
And the other question is really also related to like the revisualization question, and also basically taking into consideration the like the concept of significant versus insignificant stabilization, and then when it comes to with regard to uranium lead. So I would assume that normally when you have revisualization happening, that you want to get rid of uranium lead from the calcite source structure. It's not very complicated for them. But really what I was wondering is there any like experimental work out there where you're like actually experimentally trying to precise of your calcite and see that how that affects the ages? Yeah.
Yeah, these are, really good questions. So the questions are about, recrystallization textures, sorry. About recrystallization, if during recrystallization, it preferentially removes uranium and lead from the system, I guess making it then, less favorable to geochronology. And for that question, I would say, I mean, whatever you dissolve is still gonna be in the fluid. And I don't think that it's really about the crystallization or dissolving it itself, but let's say that the fluid dissolves the calcite. So it's gotta be something like a reductive fluid or like an acidic fluid, right? But then if it's gonna reprecipitate it, is it still gonna be reductive? Or is it gonna be oxidative whenever it reaches the point where it's gonna recrystallize something? I think that would be the bigger controller on whether that recrystallization would be favorable, because I think it's the uranium-4, the reduced uranium is going to be more favorably incorporated in the calcite than the uranium-6 or the oxidized uranium. So I always get those things backwards though, so don't quote me on that, but I think you know what I mean. It depends on the oxidative state of the fluid itself, whenever it actually precipitates it. Now, as far as if anybody's done any studies on dissolving or recrystallizing these, not to my knowledge, I don't think anybody's done that. Again, this is still like a pretty new field, and there's a ton of work that still needs to be done on the geochronology of calcite in general. So I think that's a great project idea. Yeah. Anybody else? Okay, Bruce telling me to cut it off, so. Thanks, everybody.
No, just leave it in the well.
For the data.
Yeah.